Hello gentlemen, welcome to section 1.4, graphing motion, distance, velocity, and acceleration. Please take notes, pay attention. This chapter or this section focuses on changing speed. We're going to first talk about Galileo Galilei. He was an Italian scientist who was the first to apply mathematics to the concept of changing speed. This is exactly what you guys did in your investigation. You used motion detectors to measure a change in velocity, which is a change in your speed. Now, Galileo described the change in velocity over time as acceleration. You guys already know that. Acceleration can be described as how fast the velocity changes. And velocity can be described as how fast an object is going, which is its speed, in a specific direction. Velocity depends on both speed and direction. Velocity, thus, is defined as a vector quantity. A vector quantity is a quantity that has both magnitude, which is its size, and it has direction. So examples of that, in this case, are velocity and acceleration. Velocity depends on speed, which is a magnitude and direction, and velocity defines acceleration, ergo making acceleration a vector quantity as well. Now, we know that in order to define acceleration, you have to talk about velocity, and velocities can change. When velocities change, accelerations change. Now let's talk about ways in which velocity can change. Velocity can change when you speed up, meaning your magnitude increases. You go from 25 miles per hour to 35 miles per hour. Your magnitude increases. Or you slow down, your magnitude decreases. Or velocity can change when you turn. When you turn, you change directions. And by definition, velocity is, includes both magnitude and direction. So if you change direction, you are changing your velocity as well. Now, when you change direction, when you slow down, you'll call that a decrease in your velocity. And when your velocity decreases over time, oftentimes people call that deceleration. But in physics, we don't call it deceleration. We call it a negative acceleration. So we're not going to use the term deceleration. If I use it, correct me. So in physics, we call it a negative acceleration. But if we're speeding up, if we're increasing our velocity, we call that a positive acceleration. Now, Galileo defined changing speeds in terms of mathematics. So let's look at that. So we're going to describe acceleration using an equation. From your investigate, you've kind of figured out that acceleration, which is little a, lowercase a, is equal to the change in velocity divided by the change in time. So how you're changing velocity in a span of time. Symbolically, that is delta v over delta t. So your full equation is acceleration equals delta v over delta t. And if you want to manipulate this algebraically to solve for different variables, delta t or delta v, you can use this algebra circle to help you do that. Now here's an example problem. We have a car, a little toy car. It starts out at 0 meters per second, meaning at rest. It's not moving. And that's at time 0 seconds. And then it travels along for 2 seconds. It reaches a speed or velocity of 5 meters per second. It's going in this direction. My question is, what is the acceleration of this car? Now, already Cuffs model, this is my diagram, my nodes. I know that it starts out at 0 meters per second. We're going to call that V initial. V initial equals 0 meters per second. That's V and a little I here. We also know V final. V sub F equals 5 meters per second. We know the initial time is T. Initial, T sub I. T sub I equals 0 meters per second. And we know our final time, sub F equals 2.0 seconds. Unknown is my acceleration. My formula is going to be the formula stated above. Acceleration is equal to the change in velocity divided by the change in time. Now this delta here, this change is really important. That's where we get this initial and final talk here. So let's talk about that down here. So acceleration is equal to delta v over delta t. Now delta v means a change in velocity. So it's my final velocity subtracted by my initial velocity. Or sorry, my initial velocity subtracted from my final velocity. So we have final velocity, Vf minus Vi. And the same procedure happens down here with time. Final time minus initial time. We plug those values in. My final velocity was 5 meters per second. Subtracting from my initial, which was 0 meters per second, divided by Tf, which was my final time. It took 2 seconds that I traveled, minus 0 seconds. That's what I started with. And I simplify. 5 minus 0, we know that's simply 5 meters per second. And 2 seconds minus 0 seconds is 2 seconds. When we divide this, our units for acceleration are a little different than velocity. When we do this, 5 divided by 2, we get 2.5 meters per second squared. The seconds is squared here. We'll talk more about that in our next class when we practice these problems. Now this is describing it using an equation. We can also describe using graphs, as we did in our investigator. So to describe acceleration using graphs, we have this picture here. Now the first one, A, is a distance time graph of a constant acceleration. So distance versus time, we know the slope of a distance time graph is the velocity. But from that velocity, we can also figure out the acceleration. Now, the slope of this is my velocity, but it's curved. So how do we find a given velocity at any point in time? When we do, we pick one spot here and we say, well, I want to find the velocity at that point. We have to find the tangent line. Tangent line is a line that touches this spot at only this spot. So it goes like so and just touches this one dot here. My line's a little crooked, but you draw a tangent line that just touches that spot. And this line is the slope at that particular point. And the slope of a distance versus time graph is your velocity. So here I would take my rise over run. We know my run is equal to delta t. My rise is equal to delta d. Excuse me, that's delta d. And we know delta d over delta t equals my change in velocity, or my velocity at that point in time. This is my instantaneous speed. At this given time, at this given position, that will be my speed. And this represents a constant acceleration. Now over here, graph B, this is a velocity time graph with a constant acceleration. Here's where it seems a little more constant visually. We have a constant slope here, and we know that my rise over run is delta t, rise is delta v over delta t is equal to my acceleration. So the slope of my line here is my acceleration. And since it is a constant straight line, linear slope here, we can assume or deduce that each rise over run ratio will give the same acceleration. So this is section 1.4 in a nutshell. If you have questions, gentlemen, bring them to class. Take great notes. Peace.